Last episode, you derived and implemented backpropagation from scratch. Your network can now compute gradients and update weights. But update them toward what? That's decided by the loss function. Choose wrong, and you'll train the wrong thing.
A loss function takes your network's output and the true target and returns a single number. How wrong you are. Gradient descent minimizes that number. The loss function is literally what you're teaching the network to optimize. I'm Mahaz. By the end of this episode, you'll know MSE, MAE, Huber, binary cross-entropy, categorical cross-entropy, and focal loss. What each one assumes, when to use it, and how to implement it in PyTorch. Today, MSE, MAE, Huber, binary cross-entropy, categorical cross-entropy, focal loss, PyTorch code for every loss, and a one-table selection guide. What is a loss function? Let's be precise. A loss function L takes the network's prediction y hat and the true label y and returns a non-negative scalar. 0 means perfect prediction. The larger the number, the worse the prediction. Properties a good loss function needs. It must be differentiable because backprop needs gradients. It must be a good proxy for your real objective. And it must be numerically stable. The choice of loss function encodes an assumption about your task. MSE assumes Gaussian noise. Cross-entropy assumes categorical distributions. Get the assumption wrong, and your trained model will systematically misbehave.
Two major families: regression losses for continuous outputs, classification losses for discrete outputs. These require completely different formulas. We'll cover both families in full. Mean squared error, the default loss for regression. MSE equals 1 over n times the sum of y hat minus y squared. The squared term does two things. It makes all errors positive, and it penalizes large errors disproportionately. An error of 10 is penalized 100 times more than an error of 1. The gradient of MSE with respect to y hat is 2 over n times the sum of y hat minus y. This is exactly the delta 2 we derived in backprop. The 1/2 convention cancels the 2. That's why the 1/2 version is standard in textbooks. MSE assumes your errors are Gaussian, normally distributed around 0. If that's true, MSE is the maximum likelihood estimator. If your data has outliers, MSE will overfit them because squaring amplifies their influence on the gradient. In PyTorch, nn.MSELoss, default reduction is mean. You can also use reduction equals sum or none to get per sample losses. Use MSE for housing prices, temperature prediction, anything real valued with no extreme outliers. Mean absolute error, the robust alternative to MSE. MSE equals 1 over n times the sum of the absolute value of y hat minus y. Unlike MSE, every error contributes linearly to the loss. An outlier 10 times larger only contributes 10 times more, not 100 times more. The gradient of MAE is simply the sign of y hat minus y, plus 1 for positive errors, minus 1 for negative errors. This is a constant magnitude gradient. MAE doesn't push harder on large errors. That's its strength and its weakness. MAE is robust to outliers. A corrupted label can't dominate training. But because the gradient is constant, convergence near the minimum is slow. The gradient doesn't get smaller as you approach the answer. MSE naturally slows down near the minimum because the gradient shrinks. In PyTorch, nn.MSELoss. Use MAE when your data has outliers or when the median is a better prediction target than the mean. Medical data, financial data, and sensor data often benefit from MAE. MSE versus MAE, the comparison that decides your regression loss. MSE optimizes for the conditional mean of y given x. MAE optimizes for the conditional median. If your target distribution is symmetric with no outliers, mean and median are the same. Both losses give you the same model. When they differ, an outlier pulls the MSE model toward it because the squared gradient is large. The MAE model barely moves. Its gradient is the same for any error magnitude. This is the single most important practical difference. Rule of thumb, start with MSE. If your model systematically fails on outlier regions, switch to MAE or Huber. If you need uncertainty estimates later, MSE connects naturally to Gaussian likelihood and prediction intervals. Both are smooth enough for gradient descent. MSE has a non-differentiable point at 0, but in practice PyTorch handles this with a subgradient. Neither loss is strictly better. Task and data distribution decide.
HuberLoss, the best of both MSE and MAE combined.
HuberLoss switches between quadratic and linear based on a threshold delta. For errors smaller than delta, it behaves like MSE, squared, smooth, fast convergence. For errors larger than delta, it behaves like MAE, linear, robust to outliers. The formula: if the absolute error is less than or equal to delta, Huber equals 1/2 times error squared. Otherwise, it equals delta times absolute error minus 1/2 times delta squared. This ensures the function and its gradient are continuous at the transition point. Delta is a hyperparameter you set. Typical values: 1.0 as default in PyTorch. Smaller delta makes the loss more like MAE. Larger delta makes it more like MSE. Tune delta to match the scale of typical errors in your problem. In PyTorch, nn.HuberLoss with delta parameter, or nn.SmoothL1Loss, which is Huber with delta equals 1. Huber is used heavily in reinforcement learning. DQN uses it by default because it's robust to the highly variable rewards in RL.
Binary cross-entropy, the correct loss for binary classification.
For binary classification, y is 0 or 1. The network outputs a raw logit z. Sigmoid of z gives a probability p between 0 and 1. BCE is the negative log likelihood of the Bernoulli distribution, minus y times log p, minus 1 minus y times log 1 minus p. Why the log? Because log probability is additive across examples, and maximizing log likelihood is equivalent to minimizing cross-entropy. The minus sign converts maximization to minimization. This is maximum likelihood estimation. Critical: use BCEWithLogitsLoss in PyTorch, not BCELoss. BCEWithLogitsLoss takes raw logits, applies sigmoid internally, and uses the numerically stable log sum exp trick. BCELoss takes probabilities and can produce nn when p is very close to 0 or 1. The gradient of BCE with respect to the logit z is simply p minus y, prediction minus truth. Clean, simple, and never explodes. Use BCE for spam detection, medical diagnosis, any yes or no output.
Categorical cross-entropy, multi-class classification.
For k classes, the network outputs k raw logits. Softmax converts them to probabilities summing to 1. CCE is minus the sum over all classes k of yk times log pk, where y is a one-hot vector. For one-hot targets, this simplifies to minus log of p at the true class. Why softmax with CCE? Softmax makes all class probabilities compete. Increasing one probability forces all others down. This is the right inductive bias for mutually exclusive classes. Never use sigmoid for multi-class. It doesn't enforce the sum to 1 constraint. In PyTorch, nn.CrossEntropyLoss takes raw logits. It applies log softmax internally and is numerically stable. Do not apply softmax before passing to CrossEntropyLoss. Targets are class indices, not one-hot vectors. The gradient of softmax plus CCE with respect to the logit zk is pk minus yk, identical in form to the BCE gradient. This beautiful result is why softmax and CCE are always paired. It's not a coincidence. It follows from the exponential family structure. Why softmax and cross-entropy are always paired, the derivation. Softmax, pk equals e to the zk, divided by the sum over j of e to the zj, CCE loss. L equals minus log p at true class C. We need the gradient of L with respect to zk, the logit of class K. For the true class C, partial L over partial zc equals pc minus 1. For every other class K not equal to C, partial L over partial zk equals pk. Stacking all classes, the gradient vector is p minus y, where y is the one-hot label. That's the entire gradient, one subtraction. This is the delta 2 for a classification network, exactly what backprop uses. When you call loss.backward in PyTorch on a CrossEntropyLoss, the grad that flows into your output layer is p minus y. Simple, stable, and analytically exact. The intuition: if PC equals 1 for the correct class, gradient is 0. The network is already confident and correct. If PC equals 0, completely wrong. Gradient is -1, the strongest possible correction signal.
Focal loss, solving the class imbalance problem.
Class imbalance. In fraud detection, 99.9% of transactions are legitimate. Standard cross-entropy will learn to predict, not fraud, for everything and achieve 99.9% accuracy while being completely useless. The gradient is dominated by easy negatives. Focal loss adds a modulating factor to cross-entropy. FL equals -1 minus PT raised to gamma times log PT. The factor 1 minus PT to the gamma is small when the network is confident. Easy examples contribute little to the gradient. Hard, misclassified examples dominate training. Gamma is the focusing parameter. Gamma equals 0 gives standard cross-entropy. Gamma equals 2 is the standard starting point. Higher gamma suppresses easy examples more aggressively. Focal loss was introduced by Facebook AI research for dense object detection, RetinaNet, where background far outnumbers objects. In PyTorch, torchvision.ops.sigmoid focal loss. Or implement it yourself. It's just cross-entropy times the modulating factor. Use focal loss for object detection, medical image analysis, any task with severe class imbalance.
PyTorch implementation, every loss function in code.
MSE regression. Criterion equals nn.MSELoss. MAE regression. Criterion equals nn.L1Loss. Huber regression. Criterion equals nn.HuberLoss with delta equals 1.0. Loss equals criterion of y hat, y true. Binary classification. Criterion equals nn.BCEWithLogitsLoss. Pass raw logits, not sigmoid output. Targets are float, tensor of zeros and ones. Multi-class classification. Criterion equals nn.CrossEntropyLoss. Pass raw logits. Targets are long integers, class indices. The training loop is identical for all losses. Optimiser.0grad. Y hat equals model of x. Loss equals criterion of y hat comma y. Loss.backward. Optimiser.step. Only the criterion line changes. One critical detail. CrossEntropyLoss and BCEWithLogitsLoss both expect logits. Never add a sigmoid or softmax to your final layer when using these losses. The losses apply the activation internally for numerical stability. Adding it externally causes gradient issues and slower convergence.
The loss selection guide. One table, every use case covered.
Regression, no outliers. Use MSE. Fast convergence, Gaussian assumption. Regression with outliers. Use HuberLoss. Robust and smooth. Regression, median preferred. Use MAE. Robust, slower near minimum. Binary classification. Use BCEWithLogitsLoss. Always. Multiclass, mutually exclusive. Use CrossEntropyLoss. Always. Multi-label, each output independent. Use BCEWithLogitsLoss per output. Class imbalance severe. Use focal loss with gamma equals 2. When in doubt for classification, start with cross-entropy. It's the theoretical optimum for maximum likelihood estimation on categorical distributions. It has well-understood gradients and PyTorch handles it stably. What you should never do. Use MSE for classification. MSE doesn't saturate correctly at the extremes of probability, converges to wrong solutions, and produces gradients that vanish when the sigmoid is saturated. Always match the loss to the output distribution. Before episode 12, 5 checks. Check 1. You can write the MSE formula and explain why it penalizes outliers more than MAE. Check 2. You can explain when Huber is preferred over both MSE and MAE. Check 3. You can write the BCE formula, explain why log probability is used, and state why BCEWithLogitsLoss is safer than BCEWithLogitsLoss in PyTorch. Check 4. You can explain the Softmax CCE gradient derivation, why the gradient is P minus Y, and what that means intuitively. Check 5. You can state the problem focal loss solves and what the gamma parameter controls. 5 checks. All pass. Episode 12 awaits. Optimisers. SGD, Momentum, RMS Prop, Atom, Atom W. The algorithms that use the gradients and losses you now understand. Recap. Loss functions in 1 minute. MSE. Regression, Gaussian noise, outlier sensitive. MSE, regression, robust, optimizes median. Huber, regression, robust, and smooth. Delta controls the switch. BCE, binary classification, BCEWithLogitsLoss, logits in. CCE, multi-class, CrossEntropyLoss, logits in. Gradient equals P minus Y. Focal, class imbalance. Suppress easy negatives with gamma. Your challenge: train with MSE, MAE, and Huber on regression data. Train a binary classifier with BCE. Plot all 4 loss curves. Post which converged fastest. The loss function is not a detail. It is the objective. Your network will become exactly what you measure. Measure the wrong thing, and you'll get the wrong model.
Now you know the full picture. Forward pass computes output, loss measures error, backprop computes gradients, optimizer updates weights. Next episode, the optimizer.
Episode 12, SGD, Momentum, Atom, Atom W. Why Atom almost always wins, and when SGD with momentum actually beats it.
Subscribe. Do the challenge. See you in episode 12.